All right. A couple of things before we get started. First, I forgot to give you guys a end of quarter survey at the end of 3:35, and I also forgot to make it out before this class. So you're gonna have like a little maybe 3 to 5 minute survey to do at the beginning of Friday's class about what you did last quarter. Hopefully you can remember stuff. Sorry, I just need to get it done. Second, I'm yelling at me for forgetting to do it. Second item of business, and I guess I could talk about this when we cover the syllabus. Man, some of you guys have way too much faith in ChatGPT. Using ChatGPT for the theoretical questions on your exams, it does not know shit about how transistors work for the most part, as evidenced by you guys' answers, which were wildly wrong for a lot of things. So I'm not trying to discourage you from using ChatGPT to help. I'm asking you to fact check ChatGPT when you choose to use it, because it was wildly wrong about how to mitigate the effects of channel length modulation by saying, make the channel shorter. No, very much no. Highly, highly, highly not no. Channel length modulation is a change in the relative length due to a change in the voltage. If you make the channel shorter, that makes the channel length modulation coefficient larger, which is doing the exact opposite of making it less important. Okay, so there's just some very, very basic things that ChatGPT does not currently understand. So maybe, use that, but also a textbook, and then probably just take the textbook's answer. Anyway, all right, let's go through the syllabus. A couple other things that had weird results as well that you guys put, but I don't remember what they were off the top of the head. All right, so obviously you all know who the hell I am. You largely know where my office is. My office hours this quarter are going to be Tuesday through Friday, 1:30 to 4. I'm going to be doing the Eta Kappa New circuits tutoring this quarter because I'm not as wildly overloaded as I usually am. So Tuesdays and Thursdays from 2:30 to 4, I'll be downstairs in Nefkin 105. So it'll be me, and I don't know, maybe I can actually convince some of the Honor Society students to actually show up. We'll see. You're all aware of my email address and all that kind of crap. Usual stuff. If the class needs to go to Canvas and Zoom because of a weather event or whatever, we're going to do that. In this class, here's a bunch of words. Effectively, we're going to be looking at multi-transistor circuits. We are going to be looking at how transistor amplifiers specifically respond when we tweak the frequency, connect feedback systems, all of that kind of good stuff. So it's just taking what we learned at the end of 335 and going into much greater detail about how all of those techniques and stuff are applied, both in discrete circuits and in integrated circuits. The official textbook is once again Smith and Cedra's Microelectronic Circuits, 8th edition. Doesn't particularly matter which textbook you use. If any textbook, once again, I'm recording all of my bullshit, so you have that at your leisure. Disability disclosure stuff, same as every other quarter. If you have the opportunity to get extended time, you should. Although, actually, now that I'm thinking about it, it's really not going to make any difference in this class. We'll get to that in a moment. Class attendance is the same thing as normal. Officially, show up. Unofficially, do what you want. You're adults. Honor code, same as before. Academic misconduct, same as before. Homeworks, same as before. That being said, wow, you guys were annoying the shit out of me at the end of last quarter. And turning in wrong assignments and this, that, and the other. So I have it set up such that you get one crack at every assignment, and that's it. So leave me the hell alone and turn it in correctly the first time. Jeez, friggin' Louise, you guys were so bad at it. Like, so many of you just turned in like the completely wrong assignment to the wrong submission portal, all of that kind of stuff, driving me and poor Lindsay out of our damn minds. So do it correctly, sweet mother of God. All right, quizzes. I reserve the right to give a quiz, but I'm too lazy, so I'm probably not going to. Projects, there's going to be, I think, 3 projects for this class. I'm going to try to get the first one up here pretty shortly, actually. And you'll need to do it within a week or so, just because you're going to need to use your results from that for later on in the class. Exams, 3 tests, they're all completely take home. Yeah, I don't know that you I feel like once you see the first one, you might be like, oh shit, I wish we had normal people tests. But yeah, all 3 of the tests in this class are going to be take-home exams. All of them, I would argue, each question should probably take between an hour and a half. 4 to 5 questions per test. 4 hours. Anyway. So yeah, you're gonna be expected to have to use computer tools and all of that kind of good stuff for every single question that I ask you in this class for the most. All right. The all exams have a no cell phone policy doesn't really make any sense in this context. I guess I could have deleted that, but I forgot to. Whatever. Homeworks are 25%, design projects 15%, each exam 25%. The weight of the exam on which you receive the lowest score is reduced to 15%. Standard 10-point grading scale, normal stuff about I can change the syllabus if I want to, merchant notification stuff, COVID-19 policy, counseling services, AI tools and usage, blah, blah, blah. And then our tentative course schedule, which some of you guys I heard talking about, you don't know what the hell current theirs are, nor should you at this point. However, by the end of Friday's lecture, you should. So anyway, I've already got all of the due dates and all that kind of stuff for the exams put in. So I'm going to try to get like exam 1 up this weekend so that you can literally start working on some of that stuff now and just work on that throughout the duration of the module that we're working on to be finished up by midnight on each exam day. We won't be having classes on those exam dates officially, but I'll be here to answer any questions that you might have. Just giving you fair warning, if you're starting the test on the day that the exam is due, you're doing it very wrong. Okay, like wildly, wildly wrong. Okay. All right, so I could not find my old notes for the material that I wanted to cover today, so we're just going to kind of wing it. I don't think we'll be here for the full hour and 15. I'm sure you guys are super broken up about it. All right. So let's call this an introduction to multi-transistor circuits. So one of the first amplifiers that we looked at was the common emitter amplifier, and its MOSFET equivalent was the common source amplifier. We'll look at a common source here just because it's going to make the math ever so slightly easier, right? So we had something like this, where we had some supply voltage VDD, some drain resistance. We took our output voltage here at the drain. And to make our lives even easier, let's not worry about any source degeneration here. We applied our input voltage at the gate drain. And obviously, or maybe not obviously, but hopefully you guys remember that the DC operating point of this input voltage was typically established by a simple voltage divider network on the input side and all of that kind of good stuff. Okay. So for the small signal portion of what's going on here, the biasing of this resistor is effectively just established by the resistor RD, right? So we have some voltage here VDS, we had some voltage here, some DC voltage, VGS like so, and Vout could easily be thought of as simply VDD minus whatever drain current we had flowing through our device times some resistor RD. And we talked a bit about how the value of that resistor RD was important, because as an amplifier, the voltage gain of this system is negative GM times R naught in parallel with RD, right? So the size of that resistor RD influences the DC operating point of this node particularly by this relationship. And it's also important to the gain of our amplifier. It's also important to the output resistance and stuff like that as well, but we're not going to worry about that bit too much, right? So this actually brings me to something I noticed on some of you guys' design problems. You just chose an arbitrarily huge RD resistor to give yourself a ton of gain, not paying a lick of attention to the fact that your transistor was deep into the saturation region in order to make that work out, so that you would have gotten actually a much larger gain by putting your device in saturation region using a much smaller resistor. But anyway, that's just, I didn't explicitly say that you needed to keep the transistor in saturation. That's my bad. I will add that to every damn problem now. Anyway, so the size of this resistor influences the gain, but it also influences effectively the amount of headroom that we have available, right? And that's something that we talked about earlier. If we make this resistor RD too large, we can wind up accidentally pushing our device into and out of the triode region, depending on what part of the cycle that we're in. We can also see here that this resistor RD, is it making our voltage gain larger or smaller? I would argue that it's making it smaller, because typically speaking, the value of the internal resistance R naught due to channel length modulation should usually be larger than the resistor RD that's used to bias this network, at least if you're trying to maintain that the device stays in the saturation region of operation, right? So what engineers have done is figured out a way to effectively get the results of a resistor RD here without actually using a resistor. So think about this instead. Instead of putting a resistor there, what if we put a current source? In this case, our output voltage is literally just going to be this voltage VDS, right? Why is that important? There's no RD, so really this voltage can kind of float. It can go from anywhere like as low as whatever this I bias forces it to be, all the way up to damn near VDD without any real issue. Okay. So if we were able to come up with some sort of ideal current source to bias these with, we would have a much larger voltage gain. So let's talk about what that voltage gain would look like. So our voltage gain for this guy, and you could derive this very easily if you were so inclined, would simply be negative GM R naught. Okay. This is what's known as the intrinsic gain of the amplifier, and it is literally the largest gain that this amplifier configuration is possible or is capable of achieving. Okay? Can never get larger than that. So we get a higher gain and we get a larger allowable output voltage swing without running the risk of pushing our device into the triode region. How might we go about physically implementing a current source? Transistor, absolutely right. So because we don't have access to an ideal current source literally ever, we effectively put a practical current source in its place. Or that practical current source is literally nothing more than a transistor. Now, I am intentionally not specifying whether this is going to be an NMOS or a PMOS transistor here yet, because we're going to talk about what the implications are. But this guy down here that's doing the amplification, I'm intentionally specifying as an NMOS to keep up with what we had been doing previously. I'm going to call this transistor M1. I'm going to call this transistor M2. I'm going to call this voltage V bias 2, and it should be fair. Let's put this as V out. It should be fairly obvious that whatever drain current is being carried by transistor M2 must also be carried by transistor M1, at least as long as I leave this output node open circuited. Right? There's literally nowhere else for that current to go. So now let's talk about whether that transistor M2 should be an NMOS device or a PMOS device for this particular configuration. Anybody have any thoughts? James.
I know that they usually print them on circuit for the PMOS and PMOS, but
so typically speaking, that top transistor will be a PMOS current source, but it doesn't have to be, okay? So let me explain why it doesn't necessarily have to be, okay? So effectively, all we're doing with this guy up here is we're saying effectively that we have a voltage controlled current source, okay? Where we know that our drain current ID2 is going to be 1/2 mu Cox times, I'm going to call it VGS2, but it might be VSG2, minus VTH squared, 1 plus lambda VDS, right? So as long as we could make sure that this voltage between here and here is sufficient to have this guy on and in saturation, there's nothing stopping us from putting an NMOS transistor there. However, since this is an amplifier, the voltage at the source of transistor 2 would constantly be changing, which is potentially problematic, right? Because that means VGS is going to constantly change, which means, and this relationship is going to get kind of wonky real fast, right? Whereas if instead we put this as a PMOS device, this would change to VSG, This would change to the absolute value. This bit right here would change to VSD. And this voltage, VSD2, effectively remains constant all of the time, right? Because VDD is a DC voltage and V bias 2 is a DC voltage. So this part of our current is effectively fixed. There's still going to be a little bit of play because the drain source voltage for this particular transistor is going to change as our operating point is perturbed due to the amplification. But it's not going to be nearly as large of a change as what we were seeing from this guy right here. Another reason why we probably don't want to put an NMOS device up top is because our gate and our source are most assuredly at very different voltages, which means in the case of an integrated circuit that we are going to have to take into account body effects. Whereas if we put a PMOS device up top, we don't have to worry about body effect literally at all because those things are constant. Right? All right, so let's look at how this circuit behaves from a small signal perspective. Let me scroll down here. So I'm going to put this dashed line here, where everything below the dashed line is going to be our NMOS small signal, and everything above the dashed line is going to be our PMOS small signal. So over here, I have my gate for transistor 1. This is VGS1. Here's GM1, VGS1. In parallel with R01. This guy right here is grounded. That's that. This is my source for transistor 1, and this node here is my drain for transistor 1. And then up top here, I'm going to have effectively the mirror of that. Here's my gate for transistor 2. Here's VSG2. Here's GM2, VSG2. R02. So this is my source for transistor 2. This is my drain for transistor 2. So we know that the source of transistor 2 is at VDD, large signal, which means it's going to be at ground, small signal. There is a DC bias voltage applied to the gate of transistor 2. So that means this guy right here is grounded. We know that the drain of transistor 2 is tied to the drain of transistor 1, like so. And here's where our output voltage is taken. So we now have this guy that we could do analysis on. Okay? And we could do direct analysis here, but we can also make some pretty simple simplifications here to see what's going on, right? So who can tell me what VSD2 is by inspection? 0 volts, right? Because both the gate and the source are at ground. So if this guy right here is at 0 volts, then that dependent current source up top is at 0 amps. And so all we see is the resistance R02 from our small signal perspective, right? So from that, our voltage gain for this system is just going to be negative GM1 times R0, 1 in parallel with R02. Our input resistance is still infinity. Our output resistance is just R01 in parallel with R02. Effectively, we can treat that current source connected PMOS transistor as just a resistance R02 in our small signal analysis. So that means by putting this transistor here, the one that I've circled, we actually wind up getting more headroom because really our output voltage is always just going to be between VDS for this guy and VSD for this guy. So it's allowed to move more because we're not seeing a large voltage drop over a resistor due to that current. We're seeing just a VSD that's big enough to keep that guy in saturation, whatever that is. Typically going to be significantly smaller than the voltage drop across the resistor. And we also get a larger voltage gain out of it, as well as a larger output resistance out of it, while keeping the exact same input resistance. Right? So this is a multi-transistor circuit where we're using this guy effectively as a current source, but it's also playing the role of a resistive load in our small signal analysis. Okay? Now, we can actually do the exact same thing to replace our degeneration resistors. So we might have something like this, right? So what do you think this transistor right here is doing? So when we had forced degeneration, we were typically just placing some resistance between the source terminal of our amplifier transistor and ground. Well, now we're just replacing RE with this guy right here. We already know what this thing looks like, right? So this is just RE being replaced in a small signal perspective, by a resistance R03, what impact is that going to have on the DC analysis? It's going to be pretty similar to what we saw with loading with a transmission, right? So realistically, we just want to keep this VSD large enough such that this transistor is in saturation, so that we're going to have some small voltage drop across this resistor, which is typically going to wind up being smaller than the voltage drop across a physical resistor RE would be, while providing effectively the exact same results. It also has another big impact that we're going to see in a little bit when we talk about cascode devices, in as much as the size of R03 is typically way larger than the physical resistor we would ever put in that degeneration position, which means it's going to wind up boosting the impedance seen by a very significant amount, right? So for a BJT, we saw something like when we had the generation for our I think our input resistance was something to the tune of R pi plus 1 plus beta RE. Well, R03 being much greater than RE means that that input resistance seen is going to be boosted as well by a very significant amount. So that once again, we're getting specific benefits of doing this with a transistor versus a resistor, while still maintaining basically the same level of operation. We also have the second option for connecting these extra transistors to our amplifier. So we've seen a current source connected PMOS on top and a current source connected NMOS on bottom here. We might also see what are called diode connected transistors in either of these positions. Okay. So our diode connected transistor is going to look something like this. So this is a diode connected NMOS. And this is a diode connected PMOS. And what we are going to figure out, let's call it R out, just for a lack of a better term. So effectively what we're looking for is what resistance we see when looking into the drain terminal of a device like this. So we'll look at it in the NMOS case, but it should be literally the exact same thing for the PMOS case, because the small signal models are identical. So here's our gate. Over here is our drain. Down here is our source. So in each case, we can see that the source is tied to some DC voltage, either ground or our supply voltage. So we're going to ground this guy. Our gate and our drain are tied together. So I'm going to do this in a different color so that we know it's a modification to our small signal model. But we should see that literally these two nodes are connected to each other. And what we're trying to figure out is the resistance seen looking into the drain. So we could put some test voltage source here. Let's just call it Vx for the sake of argument. The ratio of this voltage Vx to this current Ix is the resistance seen looking into the drain terminal of this device. So anybody have any thoughts on what we might see? Let's figure it out. Let's do just simple analysis, right? We can recognize something pretty easily if you think about it, and let's just do it in the same time. So I think that current Ix is just going to be the sum of Vx divided by R naught plus GMVVx. I got that simply by applying Kirchhoff's current law at the drain node. So Ix going in is equal to this current plus this current flowing out. We know that there's no current flowing this way because it's open circuit. So now I've got to figure out how to get rid of that VGS. So how is VGS related to Absolutely. That's exactly what I was about to ask you, Jeff. Yes, right. The positive polarity terminal of the voltage Vx is at this node, which is the drain and ground tied together. The negative polarity terminal of Vx is at ground. So the positive polarity terminal of VGS is at the drain, gate and drain tied together, and the negative polarity terminal is at ground. So Vx is literally just the exact same thing as VGS in this case. So that means we would have Vx over R naught plus GMVx. And from this, our output resistance R out is just the ratio of Vx over Ix, which is just R naught in parallel with 1 over GM, which will usually be about the same thing as 1 over GM, since it's typically much, much smaller than R naught. So we might use a configuration like this, where we want the generation, but we don't want a huge impact on the voltage gain of the system. So these are really the kind of building blocks that we are going to use for the duration of this class to make amplifiers do interesting things while behaving the way that they're supposed to. So I think that's where I want to stop for you. So you guys have a homework assignment that is literally just, I think, 3 MOSFET circuits with these type of transistors connected in strategic places. And my expectation is for you guys to literally use this information as well as your notes from the last quarter that just tell you how the amplifiers work and replace RD and RE with the correct representation of these guys, and then just crank out some numbers, right? It doesn't have to be any more difficult than that. We already understand how they work for a small signal with resistors there. So just treat these damn things like resistors, because that's all they're behaving as in the small signal. you guys on Friday for more interesting, and by that I mean way more difficult stuff. Yes.
Where we're fighting on there has the funding or effectively that's one of them. I'll use that for amplifying.
So let's talk about why the effective resistance of this current source is 1 over G. Okay, and why we can do it here and not necessarily elsewhere. The voltage drop across this current source is VGS. The current being supplied by the current source is GM times VGS. So the resistance of our current source is the voltage drop of our current source divided by the current being supplied by our current source. So that's going to be VGS divided by GM VGS is 1 over GM. So just in this specific instance, because there is a linear relationship between the voltage drop across this dependent source and the current flowing through this dependent source, is exactly why we didn't just model it as if it were a resistor. That's not always true, but in this specific instance, whenever we tie our gate and drain together, it will always work better. Whenever the gate and drain are tied together, it will work that way. Regardless of how everything else is connected, if the gate and drain are tied together, it's going to look like 1 over GM. So if we neglect the effects of channel length modulation, it literally is just 1 over GM. Or we acknowledge that R naught is much, much larger, it just shakes out to be 1 over GM. But more formally, it would come out to be this. And that goes into the bit about textbooks sometimes saying, well, the math is hard, so we're just going to neglect channel length modulation 95% of the time, which is, in my opinion, bullshit. And also the math isn't that hard. As I hopefully proved last quarter when we didn't neglect it literally ever and came up with relationships. I actually am working on a new set of notes on that material that I'm going to provide to you guys because I started working things in a slightly different way. Instead of starting with this is my baseline. I started with this. It actually makes finding the voltage gain, even with emitter degeneration and stuff like that, significantly easier. So instead of having that huge 2-piece thing, you get a much smaller and less terrifying 2-piece thing. It doesn't quite work out for the input resistance, but the reason for that is if we looked at, made a mistake by, I don't even know if you asked me a question related to this, but I'm still going to answer. So the small signal model, oh, go away. Actually, let me do it as a BJT. It'll make a little bit more sense. So we're calculating the input resistance of this guy. This bit over here is open circuit, right? So if we did a simple source transformation here, we could say that this would be GM R pi times V pi in series with R naught. But we could very easily see that the input resistance is literally just R pi plus R. Now, usually we would think that connecting a resistor at the output, so on the collector side of this thing, shouldn't impact the input resistance because it hasn't in literally any other case. However, putting a resistance between the collector and AC ground or supply voltage actually closes a path here, which means that this part is going to contribute to the input resistance where it doesn't in the open circuited configuration. That's the only thing that literally prevents you from doing everything that we did, how I did everything in the last class. This is the only difference. And it's a pretty easy to explain why it behaves differently. As soon as you close this path, that contributes. So with that explanation, it actually turns like several pages of math into exactly what we were doing last quarter. A quick analysis of this simple circuit, and then throw that into our way to calculate like the voltage gain with that resistive path closed and all of that kind of good stuff. It actually makes it much easier. And I've never seen a single textbook do it that way, so maybe I can make a publication out of it. We'll see. If it gets you the exact same result and makes the math less terrifying, why wouldn't we use it? That's my argument. So, anyway. Yeah. Yeah, and I mean, someone has to have thought of it before, because I mean, this isn't, it's literally just using a practical amplifier model to avoid doing a bunch of unnecessary circuit analysis. Like, that's not remotely new. Just maybe, perhaps no one ever thought of it in this specific context. I don't know. Probably somebody else has thought of it already, but whatever. All right,